Right now, Earth is moving through a region of space where galaxies are 20% rarer than they should be, not slightly rarer, not a measurement that sits at the edge of statistical error, 20% below the cosmic average in every direction, out to a distance of roughly 1 billion light-years. This region has a name, the KBC Void, and astronomers confirmed its existence in 2013. Most people have never heard of it. That matters, because living inside this structure may be distorting nearly every major measurement we have ever made about the universe. The speed at which space expands, the age of the cosmos, the distribution of matter across billions of light-years. All of it potentially skewed by the fact that we happen to reside inside one of the largest, underdense regions ever observed. The story of how we discovered this, and what it means for our understanding of everything, begins with 3 astronomers counting galaxies. In 2013, Ryan Keenan, Amy Barger, and Lennox Cowie were conducting a systematic survey of galaxy positions across billions of light-years. They examined roughly 35,000 galaxies, mapping their locations in 3 dimensions, using measurements of how much each galaxy's light had been stretched by cosmic expansion. It was careful, methodical work, and the results were wrong. Everywhere they looked, in the vicinity of Earth, there were fewer galaxies than expected. Not in one direction, not at one distance, everywhere. The deficit stretched outward, symmetrically, forming a roughly spherical region of below-average matter density, with our galaxy sitting near its center. The researchers checked their data multiple times. They cross-referenced independent galaxy surveys. They examined the sky from different angles. The pattern held our galaxy sits inside an underdense bubble of space, approximately 2 billion light-years in diameter, with a matter density roughly 20% below the cosmic average. The finding earned a name combining the initials of its 3 discoverers, the KBC Void. The name sounds almost casual. There is nothing casual about what it represents. To understand why the KBC Void is so significant, you first need to understand what cosmologists expect the universe to look like at large scales. The standard model of cosmology, built on decades of observations and simulations, predicts that when you zoom out far enough, the universe should be roughly uniform. Galaxies cluster together. Empty spaces form between clusters. That is expected, but those clusters and voids should blend into a smooth average when you average over scales of several 100 million light-years or more. A region 2 billion light-years wide with a 20% matter deficit is not consistent with that smoothness. Computer simulations of how the universe evolved from the Big Bang rarely produce voids anywhere near this large and this empty. When researchers run thousands of simulated universes and search for voids comparable to the KBC Void, they find almost none. Some analyses estimate that such a structure represents a 10 sigma deviation from the expected density distribution. In statistics, a 5 sigma result means there is less than 1 chance in a million that the result is random noise. A 10 sigma result is so improbable that you would need to observe trillions of observable universe-size volumes before expecting to find even a single example. Yet, here we are, living inside one. That statistical improbability is not just an abstract curiosity. It immediately raises questions that cut to the core of modern cosmology. If we reside in such an unusual location, does that bias every measurement we make? When we point our telescopes at distant exploding stars to calculate how fast the universe expands, are we seeing the universe's true expansion rate or a locally distorted version? When we estimate the age of the cosmos from the expansion rate, are we calculating correctly? The void hypothesis turns out to offer a possible answer to one of the biggest unsolved problems in modern physics, the Hubble tension. For years, cosmologists have measured two different values for the universe's expansion rate, known as the Hubble constant. One method looks at the cosmic microwave background, ancient light from when the universe was only 380,000 years old. This light encodes information about the early universe's density and expansion. Running that data through cosmological models produces an expansion rate of about 67 kilometers per second. That means for every of distance, roughly 3.3 million light-years, space expands at 67 kilometers per second. A second method uses nearby objects with precisely known brightnesses, type Ia supernova and Cepheid variable stars, as cosmic measuring sticks. Astronomers compare how bright these objects should be against how bright they actually appear, derive their distances, and combine those distances with redshift measurements to get the expansion rate directly. This local method consistently produces a higher number, about 73 kilometers per second per megapascal. The difference is 9%. Both measurements are remarkably precise, with tiny error margins. Both should give the same answer if our cosmological framework is correct. They do not. The discrepancy has reached 5 sigma statistical significance, meaning there is less than 1 chance in a million. It is a random fluctuation. This is what physicists call the Hubble tension, and it represents a genuine crisis in cosmology. The KBC Void provides a natural explanation. When we measure the expansion rate using nearby supernova, we are measuring from inside the void. The void's low density means less gravity pulling back on expansion locally. Additionally, the denser matter surrounding the void in the filaments and superclusters at the void's edges gravitationally attracts galaxies within the void, adding extra outward velocity. Galaxies inside the void appear to recede faster than they would in a typical region of the universe. We are not measuring the universe's true expansion rate. We are measuring the expansion rate plus the void's peculiar velocity field. When scientists model how a void of the KBC's size and depth would affect local measurements, they find it could boost the apparent expansion rate by exactly the amount needed to match observations. But this realization carries an uncomfortable implication. If the void explains our local measurements, then those measurements are systematically biased by our location. Every measurement you have ever heard about how fast the universe expands might be off, not because astronomers made mistakes, but because we are measuring from inside a cosmic structure that distorts the signal. Some scientists resist this conclusion because it appears to violate a foundational assumption of cosmology, the cosmological principle. This principle states that the universe is homogeneous and isotropic at sufficiently large scales. Homogeneous means the same everywhere. No location is special. Isotropic means the same in all directions. Together, These assumptions allow cosmologists to model the entire universe using relatively simple equations, because any patch of the cosmos should be statistically equivalent to any other dot. Void seems to contradict that directly. It suggests our location is unusual, which runs against the entire intellectual trajectory of modern science. Science has progressively removed Earth from any privileged position. Copernicus showed that Earth was not the center of the solar system. Later work showed the solar system was not the center of the galaxy. The galaxy was not the center of anything. The cosmological principle is the final expression of that trend. Not only is Earth not at the center, there is no center, because every location in the universe is equivalent, and now we are supposed to accept that we happen to reside inside one of the most statistically anomalous structures in the observable cosmos. Yet the evidence keeps mounting. The void exists. Our measurements disagree with predictions. The void's effects match the discrepancy. Whether or not we find the implications comfortable, the universe may literally be presenting us with a distorted picture of itself. To understand how a region of empty space can warp measurements made trillions of kilometers away, you need to understand how gravity behaves inside a void, and in particular, how it does something that feels counterintuitive. Gravity inside a cosmic void pushes outward rather than inward, not because gravity reverses, but because of geometry. Imagine standing in a shallow valley surrounded by mountains. Gravity pulls you toward the mountains, which means pulling you away from the valley center. Inside the KBC Void, galaxies experience exactly this effect. All the mass is outside the void, in the surrounding filaments and superclusters. That exterior mass gravitationally attracts galaxies within the void, pulling them outward toward the denser regions beyond the edges. The result is a systematic outflow, a pattern of galaxies accelerating away from the void's center, driven not by some exotic force, but by ordinary gravity acting on an unusual geometry. This outflow is measurable. Astronomers can track galaxy velocities using redshift measurements combined with distance estimates. When they map velocities around known voids, the pattern is consistent and clear. Galaxies near void centers are moving faster outward than cosmic expansion alone predicts, with the effect strongest near the void center and weakening toward the edges, where density increases. For the KBC Void specifically, the outflow adds hundreds of kilometers per second to galaxy velocities within the void. Our own galaxy participates. The Milky Way is currently moving at roughly 600,000 miles per hour away from the nearby local void, a motion distinct from the general expansion of space and driven entirely by this gravitational imbalance. This high speed is itself evidence for the void. If we lived in a typical region with average density, our peculiar velocity would be much smaller, perhaps 100 to 200 kilometers per second at most. The fact that we are moving so fast indicates strong gravitational gradients in our vicinity, exactly what you would expect from being near a large underdense region. The velocity is consistent with the void hypothesis and would be difficult to explain without it. That said, the Milky Way's total motion through space is a composite of several gravitational influences. We are moving away from the local void at about 600,000 miles per hour, We are simultaneously falling toward a rich concentration of more than 2,000 galaxies about 60 million light-years away, which adds another velocity component of roughly 250 kilometers per second. We are also gradually falling toward Andromeda, with which the Milky Way will collide in about 4 billion years. Adding all these components together, the Milky Way's total peculiar velocity relative to the cosmic microwave background rest frame comes out to about 627 kilometers per second. That total velocity is exactly what astronomers measure when they look at the dipole pattern in the cosmic microwave background. Temperature map the slightly warmer hemisphere toward we are moving and the slightly cooler hemisphere behind us. These motions matter because they complicate cosmological measurements in ways that are difficult to fully untangle. The void influences more than just our galaxy's velocity. It shapes the entire velocity field of our local cosmic neighborhood. When scientists measure the motions of galaxies out to distances of 250 million light-years, they find bulk flows, large-scale, coherent motions of galaxy populations that exceed what standard cosmology predicts. Entire regions of space are moving faster than they should be, flowing in coordinated patterns driven by the void's gravitational imbalance. Standard cosmology predicts that bulk flows should average out to nearly zero when measured across volumes hundreds of millions of light-years across. If the universe is truly homogeneous on those scales, there should be no large-scale gravitational gradients driving coherent flows. Observations tell a different story. Measured bulk flows reach velocities of 400 kilometers per second or more, roughly 4 times the predicted maximum, and they persist over surprisingly large distances. The Cosmic Flows Project has produced the most detailed maps of these motions to date. The observed patterns match predictions from models that include the KBC Void, flows directed outward from the underdensity toward the surrounding filaments, strongest near the void edges where the density gradient is sharpest, with magnitudes consistent with a 20% density deficit extending 1 billion light-years. This agreement is striking. Standard cosmology without the void cannot easily explain these observations. The structure that contains us goes far beyond the void itself. To appreciate our actual cosmic address, you need to understand the cosmic web, the foam-like, large-scale architecture of the universe that the KBC Void is embedded within. The universe is not a smooth distribution of galaxies. It more closely resembles a three-dimensional sponge or a foam of soap bubbles, where matter concentrates in thin sheets and filaments surrounding enormous hollow pockets. Galaxy clusters form at intersections, where multiple filaments meet, creating dense nodes packed with thousands of galaxies. Long chains of galaxy groups stretch between these nodes for hundreds of millions of light-years. Between the filaments and walls lie the voids. This architecture was not obvious until astronomers learned to measure galaxy distances systematically. For decades, galaxies appeared to be distributed randomly across the sky because the sky is two-dimensional. Galaxies that looked adjacent might actually be billions of light-years apart. Only when redshift surveys allowed three-dimensional mapping did the web reveal itself. beginning in the 1970s and 80s and accelerating through the Sloan Digital Sky Survey, which launched in 2000 and created spectacular three-dimensional maps spanning billions of light-years. Voids occupy roughly 90% of the total volume of space. Filaments and clusters make up the remaining 10%, but contain most of the mass. The universe is not filled with galaxies. It is filled with emptiness, punctuated by occasional concentrations of matter. If you could travel through a void at the speed of light, you would fly for tens of millions of years without encountering a single galaxy. The reason the universe is structured this way reaches back to the first moments after the Big Bang, during a period called cosmic inflation, which lasted for roughly 10 to the negative 35 seconds, a fraction of time that has no meaningful human analogy. The universe expanded exponentially. Quantum fluctuations during this expansion were stretched from subatomic scales to cosmic scales, imprinting tiny variations in density across the universe. Some regions were slightly denser than average. Others were slightly less dense. The variations were incredibly small, about 1 part in 100,000. Gravity amplified these tiny differences over billions of years. Denser regions attracted more matter from their surroundings, becoming denser still. Less dense regions lost matter to their neighbors, becoming emptier. Over hundreds of millions of years, this process snowballed. Small clumps merged into larger clumps, which merged into galaxy clusters, which aligned into filaments. Meanwhile, the underdense regions expanded into voids. The cosmic web is the result of gravity doing its work over cosmic time, turning barely perceptible quantum ripples into the grandest architecture in existence. The KBC Void is one bubble in this foam, but it is our bubble, and the fact that it is unusually large and unusually empty is what makes it scientifically important. Our galaxy does not sit at the void's center. Measurements place the Milky Way somewhere between 200 and 400. That sounds like a large distance, but the void extends roughly 1 billion light-years in every direction from its center, so our offset is relatively small. We are well within the underdense region in all directions. If we were positioned outside the void entirely, in one of the dense filaments, our measurements of the universe's expansion would look completely different. We would calculate a slower expansion rate. The Hubble tension would not exist. Our larger cosmic neighborhood adds another layer of perspective. The Milky Way belongs to the local group, a gravitationally bound collection of about 80 galaxies, including Andromeda. The local group sits within the Laniakea cluster, a massive structure containing roughly 100,000 galaxies spread across 520 million light-years. The name comes from Hawaiian and means immeasurable heaven. It is an appropriate description for a structure that redefines what we mean by our cosmic neighborhood. The Milky Way sits on the outskirts of Laniakea, part of a vast cosmic drainage basin where galaxies flow toward a central gravitational attractor called the Great Attractor. The entire structure moves coherently, bound together by gravitational flows that override cosmic expansion on these scales. Think of it as a watershed where matter flows downhill toward the deepest gravitational valley. Except the terrain is the curvature of space-time, rather than literal landscape. Here is the paradox that requires a moment of thought. Despite containing 100,000 galaxies, Laniakea resides entirely within the KBC Void. How can a supercluster exist inside an underdense region? The answer lies in how density is defined at different scales. The KBC Void is underdense compared to the cosmic average when measured over very large scales, billions of light years. But it is not uniformly empty. It contains filaments, which contain clusters, which contain groups, which contain galaxies, which contain stars. Structure exists at every scale within the void. The void is primarily defined by the absence of the richest superclusters and largest galaxy clusters at its center. The edges of the void, where density transitions to normal values, are hundreds of millions of light years away. Within that enormous volume, there is still plenty of matter, just not as much as there should be on average. Laniakea occupies part of that volume. It is large compared to typical superclusters, but small compared to the void itself. Laniakea is itself falling toward something even larger. The Shapley supercluster, located about 650 million light-years away, is the most massive structure in our region of the universe. It contains tens of thousands of galaxies and exerts a gravitational pull strong enough to affect everything around it, including Laniakea. The entire Laniakea supercluster is moving toward Shapley at several hundred kilometers per second. This creates a hierarchy of flows. Galaxies move toward clusters, clusters toward superclusters, and superclusters toward even larger attractors. The KBC Void modifies all of these flows by adding an outward component directed away from the void center, creating complex velocity patterns where objects simultaneously fall toward local attractors and flow away from the void's underdensity. One of the most powerful tools for confirming the void's existence and measuring its properties is a technique based on frozen sound waves from the early universe. In the first 380,000 years after the Big Bang, the universe was a hot plasma where matter and radiation were tightly coupled together. Sound waves rippled through this plasma, creating oscillations in density. When the universe cooled enough for atoms to form, the plasma became transparent, and those sound waves froze in place. The distance those waves had traveled before freezing, roughly 490 million light-years, left a characteristic imprint on how matter is distributed today, showing up as a slight preference for galaxy pairs separated by that specific distance. Astronomers can measure this scale and use it as a cosmic ruler, because the physics that produced it is well understood. By comparing the apparent size of this scale at different distances, scientists can map how the universe has expanded over time. This technique is called baryon acoustic oscillation analysis, and it has revolutionized distance measurements in cosmology. When researchers apply this technique to our local region and compare the results to predictions, they find a clear discrepancy. The void shows up as a region where the observed clustering of galaxies differs from what distant. Measurements predict exactly what you would expect if you are inside an underdense region. Galaxies within the void show redshifts that are slightly higher than expected for their distance, consistent with the outflow velocity adding to the cosmic expansion signal. This provides independent confirmation that the void exists and quantifies its depth and extent. The Dark Energy Spectroscopic Instrument. which began operations in 2021, is mapping tens of millions of galaxies with unprecedented accuracy. These measurements will allow much finer mapping of the void structure and velocity field. Within a few years, astronomers will know the void's properties to within a few percent uncertainty. That precision will either confirm the void as the explanation for the Hubble tension or reveal additional complications that require further theoretical development. The void also leaves its fingerprint on the most ancient light in the universe. The cosmic microwave background radiation fills the entire cosmos with faint light left over from the Big Bang. Its temperature is remarkably uniform at 2.7 Kelvin, just above absolute zero, but that uniformity is not perfect. Tiny temperature variations exist, typically only a few millionths of a degree. These variations encode information about the early universe's structure. Light from the cosmic microwave background has traveled for 13.8 billion years to reach us. During that journey, it passed through the large-scale structures that formed along the way, including voids. When light traverses a void, it experiences less gravitational influence than light passing through denser regions. This creates a measurable effect called the integrated Sachs-Wolf effect. As a photon falls into a slightly less dense region, it gains a tiny amount of energy. As it climbs back out, it loses energy. Normally, these effects cancel perfectly. But if the void is expanding while the photon is passing through, which happens because of dark energy, the cancellation is imperfect. The photon ends up with slightly less energy than it started with, which shows up as a temperature drop. This effect is tiny but detectable. Astronomers have identified large voids using galaxy surveys, then examined the cosmic microwave background temperature in those directions. On average, the temperature is about 10 millionths of a degree cooler than the cosmic average where voids are located. The correlation is statistically significant and matches theoretical predictions. It confirms that voids genuinely affect the cosmic microwave background, and it provides an independent observational handle on void properties. For the KBC Void, specifically, light from the cosmic microwave background passes through nearly the entire void on its way to us, accumulating the temperature deficit over the full billion light-year extent. Preliminary analyses suggest the void's presence is consistent with observed features of the cosmic microwave background, but the signal is not yet definitive. Future measurements with higher sensitivity should clarify this. The cosmic microwave background also reveals one of the most mysterious anomalies in modern cosmology, the cold spot. Discovered by the Wilkinson Microwave Anisotropy Probe, this region about 5 degrees across on the sky appears roughly 100 millionths of a degree cooler than surrounding areas. It is unusually large and cold compared to typical fluctuations expected from the early universe. Statistical analyses suggest such a feature occurs in only about 2% of simulated universes. One explanation is that a particularly large and deep void lies in that direction, creating the temperature deficit through the integrated Sachs-Wolf effect. Galaxy surveys have found evidence for an underdense region, now called the Eridanus supervoid, roughly aligned with the cold spot. Located about 3 billion light-years away and spanning roughly 1.8 billion light-years, calculations show that such a void can account for about half the observed temperature anomaly. The rest might come from a chance alignment with a cold fluctuation in the primordial cosmic microwave background. Or it might indicate the void is larger and deeper than current measurements suggest. The Eridanus supervoid raises the same questions as the KBC void. How did such a large underdense region form? Is it consistent with standard cosmology? If both the KBC void and the Eridanus supervoid are real and as extreme as measurements suggest, the existence of two such supervoids in the observable universe might still be consistent with the standard model, given statistical variance. But finding 3 or 4 would become increasingly difficult to explain. Future deep surveys will map the universe to greater distances and discover more voids, allowing scientists to determine whether such structures are as rare as standard models predict. The existence of these massive, underdense regions has led some researchers to propose that our standard framework for gravity needs revision. Einstein's general theory of relativity, formulated in 1915, has passed every test thrown at it for over a century, from predicting the bending of light around massive objects to explaining the orbital decay of binary pulsars. It forms the foundation of modern cosmology. But if the KBC void is too large and too deep to arise naturally in simulations, based on general relativity and the standard cosmological model, perhaps gravity does not behave exactly as Einstein predicted on the largest scales. The most prominent alternative gravity theory is modified Newtonian dynamics, or MOND, proposed in 1983 by physicist Mordechai. MOND suggests that gravity behaves differently when accelerations are extremely small, below a certain threshold. At high accelerations like those on Earth or in the inner solar system, gravity follows Newton's laws and Einstein's corrections exactly. But at the tiny accelerations relevant for galaxy outskirts and cosmological scales, gravity becomes stronger than general relativity predicts. In MOND cosmology, structures form more efficiently because the enhanced gravity on large scales pulls matter together more effectively. This produces richer superclusters and deeper voids compared to standard gravity. Computer simulations using MOND gravity naturally create voids as large as the KBC void without requiring unusual initial conditions. The statistical improbability disappears. The void becomes an expected consequence of how structure forms under modified gravity. However, MOND faces serious challenges. It struggles to explain the cosmic microwave background temperature fluctuations, which standard cosmology explains beautifully. MOND also cannot easily account for the amount of gravitational lensing observed around massive galaxy clusters without invoking some form of dark matter. Some researchers have developed hybrid models combining MOND with a small amount of dark matter in the form of massive neutrinos, attempting to preserve MOND's successes while addressing its failures. Other modified gravity theories introduce additional fields or higher dimensional effects that alter gravitational dynamics on cosmological scales while preserving general relativity's successes on smaller scales. Some predict that gravity becomes effectively stronger in low-density regions, like voids, making large voids easier to form. Testing these theories requires precise measurements of how matter moves in voids versus dense regions. The debate between modified gravity and Standard cosmology with a statistically improbable void remains unresolved. Proponents of modified gravity argue that repeatedly finding structures too large or too rare, according to standard models, is evidence that the models are wrong. They point to the KBC Void, the Shapley supercluster, the Sloan Great Wall, and other enormous structures as evidence that structure formation is more vigorous than standard simulations predict. Defenders of standard cosmology argue that modified gravity theories have their own problems, and that invoking them often creates new difficulties elsewhere. They prefer to accept that we live in an unusual location rather than overhauling a century of successful gravitational physics. The crisis extends even to the universe's estimated age. Current measurements based on the cosmic microwave background place the universe's age at 13.8 billion years. But if the local expansion rate is genuinely faster than the cosmic average due to the void, those calculations could be wrong. If the higher locally measured expansion rate of 73 kilometers per second per megaparsec represents the universe's true expansion rate globally, the universe would have reached its current size in less time. Calculations show this would make the universe roughly 8% younger, about 12.7 billion years old instead of 13.8 billion. That may sound like a small difference, but it creates an immediate conflict with other observations. The oldest stars in globular clusters appear to be about 13 billion years old based on stellar evolution models. You cannot have stars older than the universe that contains them. Stellar ages are measured by examining which stars in a cluster have evolved off the main sequence, the phase where stars burn hydrogen in their cores. Massive stars exhaust their fuel quickly and evolve off first. Low-mass stars last much longer. By observing which masses have evolved and which have not, astronomers can estimate when the cluster formed. Globular cluster ages derived this way consistently come out to around 12.5 to 13 billion years. The Gaia space mission has revolutionized these measurements by providing precise distances to globular clusters through parallax measurements, removing one major uncertainty from age calculations. The improved measurements confirm that the oldest clusters are indeed about 13 billion years old. White dwarf cooling times provide an independent confirmation. White dwarfs are the remnants of dead stars that cool gradually over billions of years. The coolest white dwarfs we observe have been cooling for about 12 to 13 billion years, again suggesting the universe is at least that old. These measurements do not depend on stellar evolution models, making them harder to adjust. The age tension, like the Hubble tension, might be resolved if the void inflates our local measurements. The cosmic microwave background estimate of 13.8 billion years could be correct, and the local stars would comfortably fit within that age. This resolution requires accepting we live in an unusual location, which bothers some scientists philosophically, but it avoids requiring major changes to either stellar physics or cosmological theory. Voids do more than distort measurements. They also function as laboratories for studying dark energy, the mysterious force that makes up about 68% of the universe's total energy content and drives the accelerating expansion of space. Dark energy was discovered in 1998 through observations of distant supernova. and it remains one of the deepest unsolved problems in physics. Its exact nature is unknown. It could be a cosmological constant, an unchanging energy density built into the fabric of space itself, as Einstein originally proposed. Or it could be a dynamic field that varies in strength over time and space. Voids are the ideal places to study dark energy, because they are the only regions where dark energy dominates completely. In dense regions like galaxy clusters, gravity is strong enough to resist cosmic expansion. Even on slightly larger scales in filaments, gravity slows the expansion of space locally. But in voids, where matter is sparse, gravity becomes negligible. With no significant gravitational pull to counteract it, dark energy controls what happens. The voids expand faster than the cosmic average, driven by dark energy's repulsive pressure. By measuring how fast voids expand, and whether that expansion is uniform or varies with direction, scientists can test whether dark energy behaves as a constant or whether it changes over time and space. If dark energy is truly uniform, voids should expand equally in all directions, staying roughly spherical. If dark energy has variations, or if there are unknown forces, voids might expand more in some directions than others, becoming elongated or distorted. Current measurements show that most large voids are roughly spherical, supporting the idea that dark energy is uniform. But the measurements are not yet precise enough to rule out small variations. The expansion history of voids also encodes information about dark energy's past behavior. A void that has been growing for billions of years reflects that entire history in its current size and density profile. By modeling how a void should grow under different dark energy properties and comparing those predictions to observations, scientists can constrain what dark energy must have been like across cosmic time. Early results suggest dark energy has been roughly constant over the past several billion years, consistent with the simplest cosmological constant model. But ongoing studies are refining these results and looking for any deviations that might hint at more complex behavior. What actually fills these void regions matters too. Cosmic voids are not perfectly empty. They contain dark matter, the invisible form of matter detectable only through its gravitational effects, at roughly 15% of the cosmic average density. Dark matter makes up about 85% of all matter in the universe. And while it is much less concentrated in voids than in filaments, it is present everywhere. They also contain dark energy, which, unlike matter, does not clump gravitationally and thus is present at full cosmic density, even in the emptiest regions. In voids, where ordinary matter is scarce, dark energy becomes the dominant component, which is precisely why voids expand faster than their surroundings. The interplay between dark matter and dark energy determines how voids evolve. In the early universe, matter dominated even in underdense regions, and gravity still shaped structure formation. As the universe expanded and dark energy became more important, voids began accelerating their expansion. They grow like expanding bubbles, pushing their boundaries outward, while the filaments of galaxies around them act as walls. The more a void expands, the emptier it becomes, which allows even faster expansion, a self-reinforcing cycle that dark energy drives continuously. This dynamic has long-term consequences for the universe. Voids occupy roughly 90% of the total volume of space today. In billions of years, that fraction will increase further. The filaments surrounding voids will thin out as galaxies within them are pulled into nodes, and as dark energy drives further separation. Galaxies and galaxy clusters that are not gravitationally bound to each other will drift apart and eventually lose causal contact as the space between them expands faster than light can cross it. The universe's destiny, if dark energy remains a constant, is increasing isolation, structures becoming islands, separated by ever-expanding voids. Galaxies that happen to exist within voids already experience a taste of that isolation. Void galaxies are among the most scientifically interesting objects in the universe, precisely because they evolve in an environment radically different from the dense filaments and clusters where most galaxy research has traditionally focused. Void galaxies tend to be smaller and dimmer than their counterparts in many are classified as dwarf galaxies, barely massive enough to hold onto their gas against the outward pressure from star formation. Their isolation means they rarely experience the galaxy mergers that drive evolution in dense regions. Mergers trigger bursts of star formation, feed central black holes, and transform small irregular galaxies into large elliptical ones over billions of years. Without mergers, void galaxies evolve more slowly and remain less developed. Despite this, void galaxies are not simply static or uniformly quiet. While most form stars slowly, a surprising fraction experience intense, short-lived bursts of rapid star formation. This seems paradoxical until you consider their gas content. Void galaxies are often unusually gas-rich, containing large reservoirs of neutral hydrogen that have not yet been converted into stars. In dense environments, interactions with neighboring galaxies strip away gas or trigger premature star formation, depleting the supply. In voids, galaxies retain their gas longer. When star formation does ignite, perhaps triggered by internal instabilities rather than external interactions, there is plenty of fuel available. The result is an intense starburst that consumes gas rapidly before settling back into quiescence. The morphology of void galaxies also differs systematically. Most are late-type spiral or irregular galaxies rather than elliptical galaxies, which form primarily through mergers. Without mergers, void galaxies maintain their disk structures and spiral arms. Some show remarkably undisturbed morphologies, with smooth disk profiles and regular rotation patterns. They have not been disrupted by interactions or gravitational tides from neighbors. This makes them excellent laboratories for studying how galaxies evolve through purely internal processes, without the environmental complications that dominate evolution in clusters. The dark matter halos around void galaxies are another area of active research. In voids, these halos are subject to less external gravitational influence. They remain more spherical and undisturbed compared to halos in clusters, which are often stretched and distorted by tidal forces from neighboring halos. Below a certain mass threshold, roughly corresponding to circular velocities of about 35 kilometers per second, halos in voids cannot hold onto enough gas for star formation to proceed. These low-mass halos exist but remain dark, containing only dark matter and no visible galaxies, which helps explain why voids are not completely filled with tiny dwarf galaxies. Void galaxies also tend to have lower metallicity, lower abundances of elements heavier than helium than galaxies in dense regions, though the difference is not as large as simple models would predict. Some void galaxies show chemical abundances surprisingly similar to galaxies in normal environments, suggesting that chemical evolution involves more complex gas flows in and out of galaxies than straightforward models assume. This filtering effect, where voids prevent the formation of certain types of structures, is self-reinforcing. Without rich clusters to pump energy into the intergalactic medium, without massive galaxies to drive strong galactic winds, the void environment remains unchanging. Meanwhile, dense regions continue evolving, growing richer and more complex. The contrast between voids and filaments increases over time, with voids becoming emptier and filaments becoming denser. The filtering effect has implications for life in the universe. If advanced civilizations require stable galaxies with ongoing star formation, voids might actually be more hospitable than dense regions in some respects. Void galaxies experience fewer catastrophic events like nearby supernova or gamma-ray bursts that could sterilize planets. The relative isolation provides long-term stability. On the other hand, the lower rate of star formation means fewer heavy elements available for planet formation. Void galaxies tend to be metal-poor, which might limit the types of rocky planets that can form. Whether voids enhance or diminish the prospects for life is an open question with no clear consensus. The idea of a Hubble bubble encapsulates how far the distortion from our location extends. When astronomers measure the Hubble constant using nearby objects within about 2 billion light-years, they get higher values around 73 kilometers per second per megapixel. When they use objects farther than 2 billion light-years or rely on cosmic microwave background data, they get lower values around 67 kilometers per second per megapixel. The boundary at roughly 2 billion light-years is suspiciously close to the edge of the KBC Void. This has led researchers to propose that measurements within the void are systematically affected by its presence, creating a local bubble of biased observations. The hypothesis makes a testable prediction. The measured expansion rate should vary with distance. Nearby measurements should show the highest values. As you look farther out and approach the void's edge, the measured value should decline toward the cosmic average. Beyond 2 billion light-years, it should stabilize at the lower value. This is exactly what recent observations are beginning to show. Studies using supernova at various distances find that the inferred expansion rate decreases with redshift. The trend is not yet definitive because measuring distances to very distant supernova is challenging, but the direction of the trend matches predictions from the Hubble bubble hypothesis. Breaking out of the bubble requires observing objects beyond 2 billion light-years with comparable precision to nearby objects, technologically challenging but becoming possible. Space telescopes, like the James Webb Space Telescope, can observe distant supernova with unprecedented detail. Early results suggest the far universe expands at the rate predicted by the cosmic microwave background, consistent with the bubble hypothesis. But the data remained limited. and more observations are needed to confirm the trend and establish whether it fully resolves the Hubble tension. Multiple independent lines of evidence now point to the same conclusion. Our local environment within about 2 billion light-years differs systematically from the universe at large. We live in an island of unusual properties, surrounded by a more typical cosmos. This is philosophically uncomfortable. Scientists prefer to believe their observations represent universal truths rather than local accidents. But the evidence increasingly suggests we cannot escape our local bias without looking far enough away that the void's influence fades. The question of whether the cosmological principle survives contact with the KBC void is still being argued. Defenders of the principle point out that homogeneity is supposed to apply at scales of several hundred megaparsecs or larger, and the void is approximately 600 megaparsecs across, right at the edge of that threshold. Perhaps the universe is simply less smooth at those scales than we assumed. Additionally, some analyses suggest the void's density deficit might be closer to 10 or 15% rather than 20%, which would reduce its statistical rarity substantially. An anthropic argument has also been made. Observers can only exist in certain environments. Perhaps intelligent life requires galaxies that form preferentially in moderately dense regions rather than in the densest clusters or the emptiest voids. If most observers in the universe find themselves in mildly underdense regions, then our location in a mild to moderate void is not surprising. But this argument only works if the KBC void is not as extreme as it appears. A 20% deficit pushes the boundaries of what the anthropic principle can explain away. Future surveys should help resolve these debates. The Euclid Space Telescope and the Vera Rubin Observatory will provide much better data on the void's precise extent, depth, and velocity field. If large voids turn out to be more common than currently estimated, the standard model survives but needs revision regarding structure formation. If they remain genuinely rare, we face the uncomfortable conclusion that Earth occupies a statistically anomalous position in the universe, on timescales that dwarf anything in human history. The void's future evolution points toward a universe of increasing emptiness and isolation. Dark energy is already accelerating the expansion of space. That acceleration will intensify over billions and trillions of years. Structures that are not gravitationally bound together will drift apart. The filaments surrounding the KBC void will thin out as galaxies within them are scattered further apart. The void will expand faster than the universe as a whole because it contains less matter to resist the expansion. Eventually, neighboring superclusters will lose causal contact as space between them expands faster than light can cross. Galaxies deep within voids will find themselves in increasingly empty skies. The cosmic microwave background radiation will become cooler and dimmer as its photons stretch to ever longer wavelengths. Eventually, it will become undetectable. The Milky Way and Andromeda will merge in about 4 billion years, forming a giant elliptical galaxy, sometimes called Milkomete. This merged galaxy will be the dominant structure in our local group, but the local group itself will become increasingly isolated. Other nearby groups will recede beyond our cosmic horizon within tens of billions of years. Milkomeda will find itself essentially alone in an expanding void. Star formation will gradually cease as gas is consumed or expelled. The galaxy will fade, containing only old stars and eventually just white dwarfs, neutron stars, and black holes. The night sky will darken on even longer timescales. Trillions of years into the future, stars will become rare as their fuel is exhausted. Galaxies will consist mainly of dead stellar remnants slowly evaporating into space through gravitational interactions. Black holes will dominate, slowly growing by accreting whatever material remains. Eventually, even black holes will evaporate through Hawking radiation, a quantum process that causes them to lose mass over incomprehensibly long timescales. The final state of the universe will be a diffuse sea of particles and radiation, expanding forever into darkness. Voids will have consumed everything. The last remnants of structure will dissipate into the void's infinite expanse. This bleak future is billions of years away and depends on dark energy continuing to accelerate expansion. But current observations suggest dark energy is indeed a cosmological constant, unchanging and unrelenting. If so, the universe's ultimate fate is void domination. The cosmic web we observe today, with its intricate filaments and clusters, is a temporary phase. The true long-term structure of the universe is emptiness, punctuated by isolated islands of matter that grow ever more remote from each other. We live in an unusual time when the universe still has rich structure and when voids are features rather than the dominant reality. Billions of years hence, voids will be everything. There is one final dimension to consider. If we live inside a cosmic void, are there other civilizations elsewhere in the universe facing the same predicament? This question connects to the broader search for intelligent life in ways that are rarely discussed. Galaxies need sufficient heavy elements to form rocky planets. Those elements are created by stars and scattered through space by supernova. In dense regions, star formation is vigorous and chemical enrichment happens quickly. Catastrophic events like gamma-ray bursts or active galactic nuclei, pumping enormous energy into their surroundings, could periodically sterilize planets within thousands of light years. Voids, by contrast, offer a quieter environment. Stars form at a moderate pace. Planets have billions of years to develop life. Cataclysmic interruptions are rare. The lower metallicity could be offset by the longer timescales available for chemical enrichment to accumulate. But perhaps the more fascinating question is whether a civilization inside a void would develop the same understanding of cosmology that we have. A civilization in a dense cluster would observe rich structure in every direction. Their sky would be crowded with nearby galaxies. They would easily measure cosmic expansion and the Hubble constant by observing a large sample of galaxies at various distances. For them, the Big Bang model would be natural and quickly confirmed. But a civilization deep inside a void might struggle. With few nearby galaxies to observe, measuring cosmic expansion becomes difficult. The void's effect on local measurements could confuse them, leading to incorrect conclusions about the universe's properties. They might develop alternative models, explaining their observations without ever realizing they needed to invoke cosmic expansion or dark energy. This raises the meta question of whether our own cosmology is affected. by our void location in ways we have not yet fully recognized. We think we understand the universe fairly well based on observations from within the KBC Void. But what if there are systematic biases we have not accounted for? What if the universe beyond the void looks fundamentally different from what we measure locally? Future observations extending well beyond the void will test this. If distant regions confirm our local conclusions, we can feel confident that our understanding is essentially correct. If they reveal systematic differences, we may need to revise our entire cosmological framework. This is the ultimate test of whether void dwellers can accurately understand the cosmos, or whether we are limited by our unusual vantage point in ways we cannot yet see. Astronomers are currently developing the tools to settle these questions. The Vera Rubin Observatory, when operational, will survey billions of galaxies across the sky to unprecedented depth. The Euclid Space Telescope is mapping the three-dimensional distribution of galaxies and dark matter across billions of light-years. The Square Kilometre Array will map neutral hydrogen gas across cosmic volumes, tracing the intergalactic medium in voids and filaments alike. Together, these instruments will produce far more detailed maps of the universe's large-scale structure than anything available today. These surveys will measure the exact extent and depth of the KBC Void. They will map the velocity field around and within it with far greater precision. They will determine whether the Hubble constant genuinely decreases with distance as you approach the void's edge. And they will reveal how many other supervoids exist in the observable universe, allowing statistical tests of whether the KBC Void is as anomalous as current estimates suggest. The outcome of those observations matters enormously. If the void explanation holds up, if the Hubble tension, the bulk flow anomalies, and the structure formation challenges all converge on a single coherent picture in which we happen to live in a large, underdense region, then standard cosmology survives. With the caveat that we occupy an unusual location. That would be philosophically uncomfortable but scientifically tractable. We would need to be more careful about how we extrapolate local measurements to universal conclusions. But the fundamental framework would remain intact if the tension persists even after correcting for the void, if distant measurements still disagree with the cosmic microwave background in ways that cannot be explained by our local environment, then new physics will be required. New forms of dark energy that evolve over time. Modifications to general relativity that alter gravity on cosmological scales. Extensions to inflationary models that change the initial conditions for structure formation. Any of these would represent a revolution in our understanding of the cosmos. What makes this moment unusual in the history of science is that we are genuinely uncertain which of these outcomes awaits us. We have the measurements. They disagree. We have a candidate explanation, the void, that is observationally supported but not definitively confirmed. And we have a set of theoretical alternatives that remain live possibilities. The next decade of observations should push these questions toward resolution. What is not uncertain is the void itself. The KBC Void is real. It is large. It surrounds us in every direction. The Milky Way exists inside a 2 billion light-year bubble where matter is rare, where dark energy dominates the physics of space. where galaxies move faster outward than standard models predict, and where our measurements of the universe may be systematically skewed by the very environment we measure them from. The universe that cosmology has assembled over the past century, the Big Bang, the expanding cosmos, dark matter, and dark energy, the formation of galaxies from quantum fluctuations, remains the best description of reality we have ever constructed. But the KBC Void reminds us that our location within that universe is not neutral ground. We are not universal observers looking out from an average patch of space. We are void dwellers, peering outward from inside a cosmic underdense, measuring a universe that may look different from here than it does from almost anywhere else. That is the uncomfortable truth that the KBC Void has forced into cosmology, and it is the reason this field remains one of the most actively contested and scientifically exciting in all of physics. If this kind of science grips you, the kind where a single observation can unsettle decades of careful work, where the very ground you stand on turns out to be scientifically special in ways nobody anticipated, then you already know why staying current with cosmology matters. The questions being asked right now about the void, about the Hubble tension, about the true expansion rate of the universe are going to be answered within the lifetimes of the people reading this. Subscribing to this kind of science, staying engaged with it, is how you ensure you are paying attention when those answers arrive. Because in cosmology, the answers almost always turn out to be stranger than the questions. To fully appreciate the scientific stakes of the KBC Void debate, it helps to understand just how thoroughly the standard cosmological model has succeeded at explaining everything else. Lambda, cold, dark matter, the framework built around a cosmological constant for dark energy and cold, dark matter particles, has been extraordinarily productive. It correctly predicted the large-scale distribution of galaxies before those maps were complete. It explained the precise pattern of temperature fluctuations in the cosmic microwave background with remarkable fidelity. It accounted for the relative abundances of hydrogen, helium, and lithium forged in the first 3 minutes after the Big Bang. It predicted the existence and properties of dark matter halos around galaxies before their effects were fully mapped. On scale after scale, the model worked. This track record is why the KBC Void's statistical improbability is so troubling. A model that works this well on so many independent measurements should not produce a structure as extreme as the KBC Void by chance. The void is not a small anomaly at the edge of the model's predictive range. It is a major structure sitting at a 10 sigma deviation from expectations. In any other field of science, a 10 sigma anomaly would be treated as immediate evidence that the underlying model requires fundamental revision. Cosmologists are not ignoring the void. They are fighting over it, and the fight is productive because it is forcing a careful examination of every assumption that went into building the standard model. One assumption that the void challenges in a particularly subtle way is how we calibrate our cosmic distance ladder. The distance ladder is the sequence of methods astronomers use to measure distances at increasing ranges. At the smallest scales, parallax, the apparent shift in a star's position as Earth orbits the Sun, gives direct geometric distances. At somewhat larger scales, Cepheid variable stars serve as standard candles, because the period of their brightness oscillations is precisely related to their luminosity. At cosmological distances, type Ia supernova take over, because they all explode with nearly the same intrinsic brightness and can be observed billions of light years away. Each rung of the ladder depends on the rung below it. If any calibration step introduces a systematic error, that error propagates upward and affects every distance measurement that uses it. The void hypothesis predicts that the supernova we use to measure the local Hubble constant are mostly located within the KBC void, because we preferentially observe supernova at distances of a few hundred million light-years, comfortably inside the void's 2 billion light-year span. If the void inflates their apparent recession velocities, the distances we calculate are accurate, but the Hubble constant we derive is not representative of the universe as a whole. Crucially, this explanation does not require any error in the distance ladder itself. The Cepheids are calibrated correctly. The supernova are being observed correctly. The redshifts are measured correctly. The bias enters not from a mistake, but from a real physical effect. We are sampling a region of the universe that is not cosmologically representative. This is an unusually difficult systematic error to correct for, because the correction requires knowing the void's properties, precisely its size, depth, and velocity field, which are themselves measured using the same telescopes and techniques affected by the void. It is a recursive problem that can only be resolved by observing well beyond the void's boundaries. There is a historical parallel worth drawing here. When Edwin Hubble first measured the expansion of the universe in the 1920s, he derived an expansion rate much higher than today's measurements. Subsequent work by astronomers, including Walter Baade, showed that Hubble had misidentified a class of Cepheid stars, using a calibration that was systematically off. Once corrected, the expansion rate dropped significantly. The Hubble tension today is different in nature. There is no known calibration error, but it shares the same structural feature: the question of whether a systematic effect has been missed that biases our measurement of cosmic expansion. The difference is that today's measurements are far more precise and far more carefully cross-checked than Hubble's original work. The systematic effects that plagued earlier distance measurements have been largely eliminated. What remains is either a genuine environmental bias from our location in a void, or a genuine failure of the cosmological framework, or both. Decades of work by hundreds of researchers have not produced a conventional explanation, which is why the unconventional one, that our location is unusual, has gained traction. The deeper issue is that cosmology, unlike laboratory physics, cannot be repeated under controlled conditions. We have one universe, and we observe it from one location within it. Every measurement we make is conditioned on our position in the cosmic web. When that position turns out to be unusual, it forces a reckoning with how much of what we think we know about the universe actually reflects universal properties versus local conditions. This is not a failure of scientific methodology. It is a fundamental feature of observational sciences, where the observer cannot choose their vantage point. Geologists face a version of this when interpreting the rock record, which is incomplete and locally biased. Evolutionary biologists face it when reconstructing common ancestors from incomplete fossil records. What distinguishes cosmology is that the vantage point bias might affect not just peripheral measurements, but central ones: the expansion rate, the age, the matter density, the dark energy fraction. The most important numbers in our description of the cosmos. One measurement that cuts across these uncertainties with particular clarity comes from gravitational lensing. When light from a distant galaxy passes near a massive object, a galaxy, a cluster, or a filament, the mass bends the light's path, distorting and magnifying the distant galaxy's image. By measuring how much distortion occurs and how it is distributed across the sky, astronomers can map the distribution of mass, including invisible dark matter, without needing to assume anything about how that mass is moving. Gravitational lensing surveys provide an independent check on the distribution of matter on large scales. They reveal the filaments, clusters, and voids of the cosmic web without relying on galaxy redshifts or velocity measurements. When lensing surveys are applied to the region around the KBC Void, they confirm the density deficit. The matter distribution detected through gravitational lensing shows less mass in our vicinity than in comparable regions of the universe, consistent with the void's existence, and roughly consistent with its estimated depth. These lensing measurements provide independent confirmation that the void is real and not an artifact of how galaxies trace matter. Galaxies are biased tracers. They form preferentially in denser regions. So counting galaxies underestimates how dense those regions are and overestimates how empty the void is. Lensing measures matter directly, including dark matter, without that bias. The fact that lensing and galaxy counting surveys give consistent results for the void's properties strengthens confidence that it is genuine. Future weak gravitational lensing surveys, including those from Euclid and the Vera Rubin Observatory, will map the matter distribution across the sky to unprecedented depth and precision. These surveys will characterize not just the KBC Void, but the entire network of voids and filaments surrounding it. They will determine whether the density deficit extends as far and is as deep as current estimates suggest, and they will resolve whether the outflow velocity of galaxies within the void are consistent with a 20% or a more modest deficit, perhaps. The most profound scientific question raised by the KBC Void is not about measurement accuracy or statistical anomalies, but about the nature of cosmological reasoning itself. We construct our picture of the universe by measuring from inside it. We have no external vantage point. We cannot step outside the cosmic web and look back. Every observation we make is conditioned on where we are, what structures surround us, how light has traveled through the intervening space for most of cosmological history. This was not a serious concern because the cosmological principle seemed well grounded. We were nowhere special, so our measurements should be representative. The KBC Void calls that assumption into question in a direct and measurable way. Our location appears to be statistically unusual. That unusualness propagates into the measurements we rely on to characterize the universe. Responding to this scientifically means doing something uncomfortable, treating our own vocation as a parameter to be measured and corrected for, rather than a neutral backdrop. It means distinguishing between what is locally true and what is universally true. It means being willing to revise conclusions that were drawn before the void's significance was understood. This is, in fact, how science is supposed to work. The history of cosmology is a series of such revisions. The universe was once thought to be static. Then it was found to be expanding. The expansion was once thought to be decelerating under the pull of gravity. Then it was found to be accelerating. Dark matter was once considered unnecessary. Then it became central to the Standard Model. Dark energy was once literally zero. Then it was found to make up 68% of the universe's energy. Each of these revisions was resisted at first. Each required accumulating evidence that the previous framework could not accommodate. The KBC Void and the Hubble tension represent the current version of this process. Whether they require a minor correction for our location or a major revision to fundamental physics is not yet determined. But the process of working through that question is precisely what modern cosmology is doing. The next several years will bring substantial new data from surveys that are already operating or nearing completion. The Dark Energy Spectroscopic Instrument is expected to measure the clustering of tens of millions of galaxies to precision that will allow detailed mapping of the velocity field around the KBC Void. The Euclid satellite is mapping weak gravitational lensing across billions of light years. The James Webb Space Telescope is extending supernova observations to distances far beyond the void's boundaries. Each of these instruments will provide independent constraints on the void's properties and on the global expansion rate. If the Hubble tension persists at its current magnitude, even as more distant supernovae are included, the void explanation becomes less convincing and new physics becomes more necessary. If the tension fades with distance, if the measured expansion rate approaches the lower value predicted by the cosmic microwave background, observations extend beyond the void's edge. The void explanation gains decisive support. There is also work being done on entirely independent cosmological probes that do not involve the expansion rate at all. Measurements of galaxy cluster abundance constrain how much matter there is and how it is distributed. Observations of the cosmic neutrino background, still beyond current instrument capabilities, would provide an independent check on the early universe's properties. Gravitational wave observations from binary neutron star mergers offer a completely independent method of measuring the Hubble constant, one that bypasses the entire distance ladder. Early results from gravitational wave cosmology are broadly consistent with both the high local value and the lower cosmic microwave background value, with uncertainties too large to discriminate. But future detections will improve precision substantially if multiple independent probes all converge on the same picture, with local measurements systematically high and distant measurements systematically lower, with the boundary between the two at roughly 2 billion light-years. The Hubble bubble hypothesis will be as well established as any result in modern cosmology. If the probes disagree with each other or with the void hypothesis, something stranger is happening, and the field will need to rethink its foundations more deeply. What is remarkable about all of this is that the question of whether we live in a void, question about the large-scale structure of space within about 2 billion light-years of Earth, become entangled with some of the most fundamental problems in physics: the nature of dark energy, the validity of general relativity on cosmological scales, the true age of the universe, the reliability of the cosmological principle, the origin of the initial conditions that seeded structure formation. A void is, in some sense, nothing. A region where matter is absent, where gravity is weak, where not much happens. But the KBC Void has turned out to be one of the most scientifically consequential features of our local universe, precisely because of how its existence interacts with our attempts to understand everything else. We are inside a cosmic hole, 2 billion light-years wide. This is not metaphor or speculation. It is observationally confirmed. Its existence is supported by galaxy surveys, gravitational lensing, baryon acoustic oscillations, bulk flow measurements, and the cosmic microwave background. Its effects match the Hubble tension, the anomalous bulk flows, and the discrepant age estimates. Its implications touch virtually every active debate in modern cosmology. Whether it is a rare statistical accident in an otherwise standard universe, or evidence that our models need fundamental revision, will be determined by the observations of the coming decade. The scientists working on those observations are among the most capable in the history of the field, using instruments of unprecedented sensitivity, guided by theoretical frameworks more sophisticated than anything available even 20 years ago. The answer is coming. And given what the question has already revealed about our place in the cosmos, there is every reason to expect it will be surprising to understand the full scientific context of the KBC Void. It helps to look at what cosmologists mean when they talk about large-scale structure and how we came to map it. With the precision that made the Void's discovery possible, the three-dimensional map of the universe that revealed the KBC Void was built using a technique that seemed almost impossibly ambitious when it was first proposed. Redshift surveys require observing hundreds of thousands of individual galaxies, measuring the precise wavelength of their light, and calculating how much the expansion of space has stretched that light since it was emitted. From that stretch, the redshift, you can calculate the galaxy's distance. Combine enough distance measurements with precise sky positions, and you get a three-dimensional map of where galaxies are actually located in space, not just where they appear on the two-dimensional sky. The first systematic redshift surveys in the 1970s and 80s were transformative. When Margaret Geller, John Huckra, and their colleagues at the Harvard-Smithsonian Center for Astrophysics mapped galaxies in a thin slice of the sky in the late 1980s, the result was stunning. Galaxies were not randomly distributed. They clustered along sheets and filaments, surrounding enormous empty regions. The universe looked like a three-dimensional arrangement of soap bubbles, with matter concentrated at the bubble walls and vast emptiness inside. The CFA to Great Wall, identified in that survey, was at the time the largest known structure in the universe. A sheet of galaxies stretching about 500 million light-years across. It was so large that it raised immediate questions about whether the standard cosmological framework could explain how such a structure formed. Subsequent surveys found larger structures still. The Sloan Great Wall at nearly 1.5 billion light-years. The Hercules Corona Borealis Great Wall at roughly 10 billion light-years, though that last structure's status as a coherent bound object is debated. The KBC Void fits into this context as the largest confirmed underdense structure known, identified not through its visible walls, but through the systematic absence of galaxies within it. Unlike the Great Walls, which stand out as concentrations of matter, the KBC Void stands out as an absence. its discovery required statistical analysis of galaxy distributions across enormous volumes, not looking for where galaxies are, but carefully measuring where they are not and how much they fall below the expected average. This is harder than it sounds. To identify a void accurately, you need a complete survey that covers the relevant volume without systematic biases. If your survey preferentially misses faint galaxies at certain distances, you might create apparent underdensities that reflect survey incompleteness rather than real structure. Keenan, Barger, and Cowie's 2013 analysis was designed specifically to address these issues, using multiple overlapping surveys to cross-check their results and ensure the measured deficit was real. Subsequent independent analyses using different survey data and different methods have confirmed the broad picture. The void is real. Its depth is somewhat uncertain. Estimates range from roughly 10% to 20% below the cosmic average, depending on the survey and the analysis method, but the qualitative result is consistent. We live inside a large underdense region, and that underdensity has measurable effects on our astronomical observations. The confirmation that came from baryon acoustic oscillations is particularly valuable because this technique is independent of galaxy count statistics. The baryon acoustic oscillation scale is imprinted in the distribution of all matter, not just the galaxies we can see. When the baryon acoustic oscillation scale measured locally differs from the scale measured at larger distances, it provides direct evidence for a local underdensity. The fact that baryon acoustic oscillation analyses find exactly this discrepancy adds a physically distinct line of evidence pointing to the same conclusion. Understanding the void also requires understanding the history of how voids form and what happens to matter as they grow. In the immediate aftermath of the Big Bang, the universe was nearly uniform. The density variations that would eventually become the cosmic web were present, but incredibly small variations of about 1 part in 100,000. Nothing like a void existed yet. The universe was a hot, dense, nearly uniform plasma. As the universe expanded and cooled, gravity began amplifying those tiny density differences. The mathematics of how this happens is well understood. In a region slightly denser than average, the additional mass exerts slightly more gravitational pull, drawing in matter from the surrounding area. This makes the region denser still, which draws in more matter in a positive feedback loop. Meanwhile, regions slightly less dense than average lose matter to their denser neighbors. As matter drains away, the underdense regions become even emptier, which reduces their gravitational pull, which causes them to lose even more matter to surrounding overdensities over hundreds of millions of years. These initially tiny differences grew into the structures we see today. Dense regions became the filaments and clusters of the cosmic web. Underdense regions became voids. The amplitude of this growth, how much larger and more extreme structures become over time, depends on how much dark matter there is, how dark energy behaves, and the precise statistics of the initial density fluctuations. Standard cosmological simulations, run on supercomputers and incorporating all the physics of dark matter, dark energy, and baryonic matter, reproduce the cosmic web in remarkable detail. They predict the typical sizes and depths of voids, with accuracy sufficient to match observations in most cases. The KBC Void is the exception. It is larger and deeper than simulations typically produce, which is the source of its statistical improbability. The contrast between the simulation's successes and the void anomaly is what makes the situation scientifically interesting rather than simply embarrassing. If the standard model failed to reproduce cosmic structure generally, we would simply replace it, but it succeeds almost everywhere except here. That selectivity of failure is informative. It suggests either that the KBC Void is a genuine rare event within an otherwise successful framework, or that the framework has a specific weakness in producing large-scale underdensity that its other successes have not. Exposed, distinguishing between these possibilities requires more than just deeper surveys of our local region. It requires mapping comparable volumes at many other locations in the universe to build the statistical distribution of void sizes and depths. If surveys of distant regions find supervoids as large as the KBC Void appearing regularly, the standard model's failure was a sampling issue. We underestimated the tail of the distribution. If supervoids this large remain rare in distant surveys as well, the model has a genuine problem that better sampling will not fix. This is precisely the science that the next generation of surveys, Euclid, Vera Rubin Observatory, the Dark Energy Spectroscopic Instrument, the Square Kilometer Array, is designed to address. They will map the universe's large-scale structure with enough coverage and depth to characterize the statistical distribution of voids to the precision needed for these tests. Within a decade, cosmologists should be able to say with confidence whether the KBC Void is a statistical outlier in an otherwise normal distribution, or whether it is symptomatic of a deeper failure in our models. One aspect of the KBC Void that deserves more attention than it typically receives is what it tells us about the relationship between dark matter and visible matter. Galaxies are not perfect tracers of mass. They form preferentially in dense dark matter halos, and different types of galaxies form in different environments. The relationship between where galaxies are and where matter is, called galaxy bias, is complex and scale-dependent. In a void, this relationship is particularly interesting. The dark matter density in the void is lower than average, but not as low as the galaxy density. Dark matter is present throughout the void at about 15% of the cosmic average, even where no galaxies are visible. The void's near-emptiness in terms of visible galaxies overstates how empty they are in terms of mass. A traveler moving through the KBC Void at the speed of light would encounter a very sparse population of galaxies, but would still be immersed in a sea of dark matter extending throughout the void's volume. Less dense than normal space, but not negligible. This distinction matters for understanding how voids evolve and how they affect large-scale dynamics. The gravitational potential of the void, the quantity that drives the outflow of galaxies, and the distortion of expansion measurements is determined by the dark matter distribution, not just the visible galaxies. Getting the void's gravitational effects right requires modeling the dark matter distribution accurately. Gravitational lensing surveys are valuable here because they measure mass directly, tracing both visible and dark components. The intergalactic medium within the void is also of scientific interest. Between galaxies in the void, There is diffuse gas, mostly hydrogen and helium, at lower density and lower temperature than gas in filaments. This gas is closer to the conditions of the early universe than gas that has been heated by galaxy interactions and active galactic nuclei in dense regions. Studying this gas provides a window into the state of baryonic matter before it was processed by the violent dynamics of cluster environments. Observations of distant quasars provide one way to probe this gas. When a quasar's light passes through intergalactic gas, the gas absorbs specific wavelengths, leaving dark lines in the quasar's spectrum. The pattern and distribution of these absorption lines trace the gas density along the line of sight. Surveys of quasar absorption spectra have mapped the three-dimensional distribution of intergalactic gas across cosmic volumes, confirming the large-scale structure seen in galaxy surveys and providing an independent tracer of the cosmic web. In void regions, the intergalactic gas shows lower absorption than in filaments, consistent with the lower density. The gas temperature in voids is also lower because there are fewer sources of ionizing radiation from nearby galaxies and active galactic nuclei. This cooler, less ionized gas retains a memory of conditions in the early universe that has been erased in denser environments. Future ultraviolet space telescopes capable of higher resolution spectroscopy of many quasars simultaneously will produce detailed maps of void gas across large cosmic volumes, complementing the galaxy surveys and lensing maps being built by other instruments. All of these observational threads, galaxy redshift surveys, gravitational lensing, baryon acoustic oscillations, bulk flow measurements, cosmic microwave background temperature correlations, quasar absorption spectra tell a consistent story. The universe has structure on scales larger and with greater contrast than the simplest versions of the standard model predict. The KBC Void is the most prominent local example of this excess structure, and our location within it conditions everything we observe about the final word. The final word on the KBC Void has not been written. The measurements are improving. The theoretical debate is active. The implications are still being worked through. But the discovery itself, the realization that we sit inside a 2 billion light-year bubble of below-average density, surrounded by a cosmos that may look systematically different from our local patch ranks. Among the most consequential findings in modern cosmology, it changes how we interpret our measurements. It changes how we think about our place in the universe, and it reminds us, in the most direct possible way, that science is an ongoing process of discovering that the universe is stranger, and our knowledge of it more provisional than we imagined. The void is real. Its consequences are measurable, and understanding them fully is the work of a generation of astronomers who are only now building the tools to see clearly beyond its edges. There is one more angle on the KBC Void that rarely gets discussed but is worth considering carefully. What it implies about the anthropic reasoning that sometimes enters discussions of unusual cosmological features. When we discover that we live in a statistically improbable region of the universe, one response is to invoke anthropic selection, the idea that we observe what we observe because only certain environments allow observers to exist. If living in a void were lethal to life, we would not be around to notice the void. But life clearly can exist in a void. Galaxies form here. Stars burn here. Earth exists here. The anthropic principle cannot explain away the statistical improbability of the KBC void by arguing that only rare locations permit observers. A softer version of the argument suggests that intelligent life preferentially arises in moderately underdense environments, perhaps because they offer lower rates of catastrophic disruption from nearby supernova, gamma ray bursts, or active galactic nuclei. On this view, finding ourselves in a void is not surprising because observers like us are disproportionately likely to arise in void environments. This is a legitimate scientific argument, but it requires that the void provide a specific enough selection advantage to overcome the statistical improbability. Whether it does depends on how strongly these environmental factors actually influence the emergence of intelligent life, which is not known. What the void does not require is any appeal to special positioning of Earth within the solar system, or the solar system within the galaxy, or the galaxy within the local group. At each of those smaller scales, our position appears unremarkable. It is only at the cosmic scale, looking across billions of light years, that our position becomes anomalous. This scale dependence is itself informative. Whatever produced the KBC void, it is a large-scale phenomenon, the result of cosmological scale processes operating over billions of years, not a local accident. The most scientifically productive attitude toward the void is probably the least comfortable. Treat our location as a variable that needs to be measured and characterized, not a neutral given. Every cosmological inference drawn from local measurements, the Hubble constant, the matter density, the dark energy fraction, the age of the universe, carries an implicit assumption that our local environment is representative. The KBC void tells us that assumption may be wrong at the 10 to 20% level. Correcting for it requires knowing the void's properties precisely enough to separate its effects from the true cosmic average. This is achievable. It is being worked on. The measurements needed to characterize the void's influence on our cosmological inferences are within reach of the instruments currently being built or operated. Within a decade, the correction may be routine, a standard term in cosmological analyses, like correcting for our velocity relative to the cosmic microwave background rest frame, which astronomers have been doing for decades. If that correction resolves the Hubble tension, it will be a triumph not just of observational astronomy, but of the kind of careful thinking about systematic effects that defines the best science. Recognizing that a measurement might be biased by the measurer's environment, identifying the nature and magnitude of the bias, and correcting for it to recover the underlying truth. That process is what distinguishes science from mere data collection. If the correction does not resolve the tension, it will point toward something more fundamental, new physics, a revision to our understanding of dark energy or gravity or the initial conditions of the cosmos. That possibility is both exciting and humbling, because it would mean that after a century of remarkable progress in cosmology, there are still discoveries of the first order waiting to be made. Either way, the KBC void has transformed from a curiosity into a cornerstone of the most important debates in modern cosmology. Its existence demands engagement. Its implications demand honesty about the limitations of measurements made from inside an unusual cosmic environment, and its eventual resolution, whatever form that takes, will advance our understanding of the universe in ways that go far beyond the void itself. We are inside a cosmic hole, 2 billion light-years wide. The hole is real, it is measured, it is surrounded by a universe that continues to reveal itself as stranger and more structured than our models expected. And right now, from inside this void, we are building the tools to see what lies beyond it. There is a kind of clarity that comes from understanding your cosmic address fully, not just the planet, the solar system, the galaxy, but the vast, underdense expanse that surrounds all of it. The KBC Void is not a threatening discovery. It is an informative one. It tells us that the universe is more varied at the largest scales than we assumed, that cosmological reasoning requires care about environmental context, and that the questions being actively debated in cosmology today about dark energy, about the expansion rate, about whether our models are complete, are genuine, open questions, not settled matters with a few decimal places left to fill in. The history of cosmology is a history of discovering that the universe is larger, stranger, and less centered on us than previously imagined. The KBC Void continues that tradition. We are not at the center of the solar system. We are not at the center of the galaxy. We are not in a typical region of the cosmic web. We are void dwellers, peering outward through billow-verge density space, making measurements that may carry a systematic fingerprint of where we stand. Accounting for that fingerprint is the scientific work of this era in cosmology. The answers, when they arrive, will be worth the effort. The science being done around the KBC Void right now, mapping its edges with baryon acoustic oscillations, probing its gravitational influence through bulk flows, tracing its imprint on the cosmic microwave background, extending supernova surveys to distances beyond its reach, is some of the most technically demanding and conceptually rich work in contemporary astrophysics. It combines observational precision with theoretical depth in exactly the way that the most consequential discoveries in the history of science have required. Whatever the universe reveals, when those investigations reach maturity, the KBC Void will have been a key that unlocked the questions worth asking.